Thank you very much. All right, guys. All right, let's continue. So we did actually discuss this slide on a couple of occasions. So now you know actually that adaptation, if it does not stop at one point in time by removing whatever has resulted in the adaptation in the first place, is going to result in cell injury. Now, cell injury does not need adaptation to actually to happen. It may happen right off the bat, with any kind of, enough kind of stressor to result in cell injury. As I mentioned to you before, two types of cell injury. There is the reversible one and the irreversible one. So one of the things we will actually discuss here is what is the point of no return? When does the cell actually becomes irreversibly injured? Right, so what are the causes of cell injury? The most common cause, at least this is what you will be reading everywhere, is going to be hypoxia. Okay, hypoxia with its delivery, with its lack of delivery of oxygen, is going to be the number one. This is where cardiovascular disease as the number one of mortality and morbidity worldwide, came from. But really, if you think about it, if you look deeper into it, you will realize that actually it is the free radical injury that is the unsung hero of cell injury. It is the factor that you will not see listed anywhere, but it is really, for the most part, the most common cause of cell injury. How is that? When there is hypoxia and there is interruption of the oxidative phosphorylation that is happening in the mitochondria, there will be partial reduction of molecular oxygen that will result in the formation of free radicals in the mitochondria. So right off the bat, here hypoxia and its relationship to the production of ROS, of free radicals in the mitochondria. Physical agent, let's talk about radiation. Let's say someone actually is receiving radiation therapy to a tumor. As you beam this actually light onto the tumor, the area surrounding the tumor, the tissue surrounding the tumor has water in it. The radiation is going to split the water into HO, the OH minus hydroxyl group, which is itself is a free radical. And the free radical is going to wreak havoc on nearby, in this case, malignant tissue. So it uses it as actually an example of that. Let's talk about actually chemical agent. Tobacco itself, with all the toxins and the carcinogen that it brings into the airways, is loaded with chemicals that will result in the formation of free radicals. Infectious agents, with the inflammation that they cause and the cells they bring to the site. Example of that, the macrophages and especially the neutrophils, which uses free radical as a matter of policy for killing bacteria and offending organisms. Immunologic reactions itself, again, the inflammatory cells that will be brought to the site of action. Let's talk about nutritional imbalances, such as, for example, the atherosclerosis that results from excess food intake. The result of that is going to be the deposition of LDL fat in the soft tissue. And because the macrophages will not be able actually to digest these are LDL cholesterol crystals, the end result is going to be the formation of free radicals. Genetic derangements, with something like hemoglobinopathies is also related to free radical. How? So with hemoglobinopathy, as an example, hemoglobin S, the sickle cell disease. Okay, sickle cell disease is a disease that results from a point mutation in the beta globin chain of the hemoglobin. The end result is going to be the formation of hemoglobin S. Hemoglobin S is bad for a couple of reasons. One of them is that actually it holds tight to itself, the oxygen. It does not allow for a free exchange of the oxygen in the periphery. So as a result of that, the peripheral tissue will undergo ischemia. The other thing is that it will aggregate on itself inside the RBC. So instead of the finely dispersed HbA, hemoglobin, you will see that the HbS is going to aggregate in certain areas, in the RBC, and as a result of that, the RBC is going to take a shape of what you call sickle. Well, you know what a sickle is?
Yeah.
Good. How come you know what a sickle is?
Because
You got it in HLA in your one. Excellent, excellent. Good to know that. All right. So actually, those actually sickle cells, do they have a, okay, so probably you should tell me about it. I should not be telling you about it. What do these sickle cells, what is the feature, the detrimental feature of those sickle cells? Once they become sickles, what do they do? Why do they do this? Because they have higher affinity to the endothelium, right? And as a result of that, they create microplaques, right? Especially in the smaller circulation. And what will the result in that? That's going to result in ischemia, right? And as a result of that, the areas that will undergo the ischemia, what will happen to it? Not before necrosis, the mitochondria will become weakened and the oxygen has stopped going there. So what will the mitochondria be doing? Be manufacturing ROS, free radicals. So it is somehow, again, so the underlying theme of pretty much everything, really, if you think about it, is going to be free radical injury. Of course, not all of it. In medicine, you can never say all, the minute that you see all of the above, that means wrong, because it can, most likely, it is not the case. But it is, probably the most common cause of cell injury. All right, so now, we did talk about actually that, the cell type is going to play a role actually if cell injury will happen or not. For example, if you apply ischemia to a skeletal muscle cell, it will take about 3 hours actually for it to become ischemic and die. If you apply, the same kind of ischemia to a myocardial cell, you're lucky if it lasts, 10 minutes. So the type of the cell. 2, the severity of the injury. We did talk about this before. 3, the type of the injury. There are actually types of injury that the cell will not recover from. Example, free radical injury. And then also, this condition of the cell before the injury happened. A cell that is replete with nutrients, with O2 and with glycogen, okay, and with antioxidant, will fare better than a cell that is depleted of this. A cell that has all the above will be able to have another day and to fight another day. If the cell does not have any of the above, it will have really hard time surviving the injury. All right, genetic makeup. Then there is the genetic makeup. You take the same toxin and you give it to person A and person B. Person A will take it as if there is nothing. Person B will succumb, and die as a result of that. One of the reasons for this is, a system, a detoxification system that is present in the liver, in specific areas in the liver. Where is it present in the liver? What zone in the liver cells? No, wait, how many zones in the liver do you know about? 3. Good. This is a good start. So you have zone 1, right? Which is where?
The one closest to
the one closest to the portal triads. And then you have zone 3, which is what?
the furthest one.
The one? The furthest away from the triad. Where is it? This is like you're smart, so you don't really know exactly where it is, but it is the distance. So what is it? Well, it's surrounding the central veins, right? The veins, right? So and then you have the zone 2, which is in between, correct? Where is the area that is mostly rich with this, P450 system? Zone 3. It is the zone 3. This is what you look at in a biopsy in a liver that is you're suspecting of a toxic injury. The first zone you look at is zone 3. And if it has been, damaged, you will see that those cells have dropped, have died. So why is that the case? Because, there is people who have a system that can take care of any kind of booze, any kind of toxins, any kind of really anything. They can handle anything. And then the opposite also is true. There are people who cannot take care, cannot take care of any simple kind of injury. All right, so what are the intracellular systems that are susceptible to injury? First and foremost is the ATP. The ATP is it's like money, right? If you have money, you can take care of business, correct? You don't have money, you're like that about this. Cell membrane, the patency of cell membrane is incredibly important because of one very important thing. If cell membranes allow for the influx of what into the cell, that's going to calcium, absolutely, very good. Then protein synthesis, all those membranes, all those, different, different substances in the blood need proteins to be transported. You take out, protein synthesis, that's it. Genetic apparatus, this is the brain of the cell. You take out the brain of the cell, good luck with everything else. So you can see actually that it is what you call, intertwined. Why? Let's say that actually you have a problem in the nucleus. If you have a problem in the nucleus, the mitochondria will not work because they crossed off. If you have a problem actually in the cell membranes, okay, you will see that protein synthesis itself is going to be affected as well, and vice versa. And the injury, the damage to one system is going to result in damage to the other, systems as well. All right, so now important mechanism of cell injury, starting with ATP depletion, we did talk about this. The loss of calcium, we also talked about this because it is the cofactor to all the degradative enzymes that are present in the cytoplasm. Mitochondrial damage, the mitochondria are the powerhouses of the cell. This is where all the ATP, or at least the majority of the ATP is being made. Where is it, like how many molecules of ATP does the cell hope to get, in every cycle of aerobic respiration? 38. At least this is what they say. It is 38, which is a combined actually 2 per Krebs cycle, right? 2 per glycolytic breakdown, and 34 per actually per oxidative phosphorylation. In reality, actually, it is 29 to 30 because the membranes are leaky, and as a result of that, that actually may result in a changing formula of how many you have with every cycle of aerobic respiration. Now, any damage to the mitochondria is going to be detrimental for 2 reasons. One, you no longer have ATP being produced, in the oxidative phosphorylation, the majority of the ATP in the cell. The second thing is that the components of the mitochondria will start to actually seep through the mitochondrial membrane and into the cytosol. And those actually are messengers that they are going to talk to the nucleus and tell the nucleus that the cell has reached its final destination, which is going to activate apoptotic mechanism by the nucleus. So this crosstalk is also very detrimental to this thing. Increased cell permeability, we already have talked about this. And then, the generation of the free radicals. You can see again that they are intertwined because, mitochondrial damage is going to result in generation of oxygen-derived free radical, right? Now, the generation of oxygen-derived free radical, let's say that they are coming from the outside, are going to wreak havoc on the cell membrane, okay? And they are going to wreak havoc on the mitochondria. So it is very much, what do you call it, closely connected kind of network. One system get damaged, the rest of the systems will be damaged eventually. And that will set the cell into one way into the next life. All right, we talk about 2 kinds of cell injury, reversible versus irreversible. And, the cell can revert back to normal, with the reversible one, but with the irreversible one, that's when the cell has actually severe damage of the membranes of the mitochondria or the nucleus. It's a one-way that there is no coming back from. Examples of cell injury, you will see that the first, the top 3, the hypoxic, the ischemic reperfusion, and the free radical cell injury, are very much, talking about the same thing, really. And the one is going to lead to the other. So, for example, hypoxic cell injury is going to result in ischemia. So when you go in, the good doctor, and you actually establish blood supply to that organ by stenting, for example, putting a stent, the end result is going to be what? The end result is going to be that all the good stuff that has accumulated behind the obstruction are going now to be released. What has accumulated behind the obstruction? What happened to those cells that became, ischemic? Those cells have become actually ischemic, so all their membranes become leaky. Okay, 1, 2, because no longer oxygen is being delivered. So what happened to the mitochondria? Now the mitochondria, instead of making ATP, it's making actually free radicals, right? So two free radicals, one, two, the membranes become leaky, the free radicals leak out. Okay, some of the cells are already dead. So the cells are going to be releasing not just free radical, but also they will be releasing calcium, right? And now you are the good doctor and you have come in and you have established blood supply again to the distal regions. Now what's going to happen is that this calcium and these free radicals are going to find their way not only to the site that was blocked, but because you have taken out the block, they are going to be affecting the whole region. So as a result of that, you will see that there is extension of the damaged area beyond what was originally obstructed. Okay, so this is one. And then free radical cell injury, this is part and parcel of this. Last question, go ahead and ask me.
For the hypoxia, they have less oxygen, right?
Yeah.
So how can, even if they have less oxygen, they still have oxygen, why will it be not converted into water instead of free radicals? I don't know.
Say it again.
They have decreased oxygen,
Probably no oxygen.
no oxygen. So how could, if there's no oxygen, how is it that the oxygen in mitochondria is being converted to free radicals?
Because it will not go through the full cycle. So what you have actually, you have two electrons. You have the electrons, right, that are coming from the NADH and the FADH2, and they are being delivered to oxygen to result, and so that until the end of this, cycle of oxidative phosphorylation. And they are coming actually from a high energy content of the NADH and FADH2 to the low energy content of the oxygen. So there is energy that is being transferred. This energy that is being transferred is going to be the one that is going to phosphorylate the ADP to ATP. If you have actually interruption of oxygen, which means you no longer have oxygen, this process is going to stop in the middle actually, which is going to result in the formation of the superoxide, which is the free radical. So it will stop the process in its track. It will not complete until the end. Once you have a dipping of the oxygen, which should be on the receiving end of the electrons, the process is going to stop in its track, meaning incomplete reduction, okay, of the molecular oxygen, which means the ROS will be formed. Okay, does that deliver the idea somehow? Homing on it, right? Okay, if you have a question, please keep it. You can ask me this at the end. This way, we're going to finish this lecture today. How about that? All right, so what are the causes of this? So hypoxia, as I mentioned to you, the most common cause, at least what we call the apparent cause, the phenotype, right? There's also always apparent and hidden, external and deep, if you will. This is the external cause. And below it, there are other causes of this hypoxia, including ischemia, for example. Ischemia, that's of course going to be coming actually from atherosclerosis, which is the most common disease worldwide. A major cause of death actually resulting in cardiovascular disease and strokes, major cause of morbidity as well. So what happened actually is that there is a disease of the intima, and once there is actually this atherosclerotic plaque, the atheroma that is forming, it is going to disrupt the laminar flow, right? And once it disrupts the laminar flow, that means actually the cellular content of the blood will be coming into contact with the epithelium, with the endothelium. And that's when you start to see the formation of a plug. This plug may break and travels, with the flow, resulting in an embolic event. Now, hypoxemia could be also doing the same. And here you can see actually that there is a decrease of the amount of oxygen dissolved in plasma. Where do you see that? So hypoxemia, more or less is going to be actually coming from the lung, either atelectasis. So atelectasis, that's collapse of the alveolar acini. Where do you see that? Let's say that there is a tumor that is growing on the inside, surface of the pleura, what is known as mesothelioma. This actually tumor is going to, compress the nearby tissue, emptying it of its blood, blood and air as well. So now what happens actually to the blood that is coming to the lung? The blood that is coming to the lung will not be completely aerated. Why? Because a portion of the lung is gone, okay? And what will happen to the PaO2? It's going to dip, okay? So here you have hypoxemia that results from atelectasis. Pulmonary embolus, especially if it's a large pulmonary embolus. the pulmonary embolus, for the most part, will never actually result in infarction in a young, healthy person. The reason for this is, as you guys know, there's a dual blood supply. There's the pulmonary and the bronchial circulation. Now, if it's a large embolus, something that goes actually and right on the bifurcation of the pulmonary artery, that actually may result in complete infarction. But that's very unlikely to happen. And also the condition of the pulmonary vascular bed will play a role in this. At any rate, if you have a pulmonary embolus, part of the lung is going to, again, be decommissioned, meaning there will be no circulation in that area because blood will not reach the area that are obstructed with the embolus. Meaning, again, there is a ventilation perfusion mismatch that is going to result, again, in hypoxemia. How about actually if you have a thickened alveolar wall? That also going to actually, hamper the exchange of O2 through the alveolar walls, right? So could you give me examples of processes that result in, thickening of the alveolar walls? Yeah, no, edema should be in the alveolar lumen. Fibrosis, like what kind of fibrosis? Say again? How about asbestosis, for example? That's one. Asbestosis, all the pneumoconiosis, asbestosis, cold water pneumoconiosis, silicosis, all of those diseases actually are focused on the alveolar septum. And when they happen, they are going to increase, the fibrous tissue in the alveolar septum. So at that level, at that time, trying to have exchange is going to be very hard to have a free, movement of O2 and CO2 in opposite direction, between the blood and the alveolar lumen. Okay. Now, how about hemoglobin-related abnormalities? Anemia. If everything is fine, if the vessels are fine, no problem. If also the lungs are fine, but then you have actually less RBCs and less hemoglobin, what is that going to result in? The same exact problem, because you don't have enough RBC to carry this oxygen to distal tissue. So there will be, again, hypoxia. Now, how about actually if you have a specific, special type of hemoglobin, such as, the carbon monoxide, that follows the carbon monoxide poisoning. With this special type of hemoglobin that result from this poisoning, and also other types of hemoglobin as well. The problem is that, they will hold the oxygen dear to their heart, and they will not let it, go freely into the distal tissue. And that's bad, because then the distal tissue are going to suffer ischemia. And, we see that in a lot of different, hemoglobinopathies, having the same exact, feature, that it binds too closely to the oxygen, and it does not allow its, free dissociation in the peripheral tissue. All right, so, once you have, tissue hypoxia, what happened to the synthesis of ATP? The synthesis of ATP in the mitochondria will start to dip. And, the ATP are important for pretty much everything that happens in the cell. Any kind of production of any components of the cells, need ATP. All right, so ATP production happens through the oxidative phosphorylation. So with aerobic respiration, you have actually the Krebs, you have the glycolytic pathway, and you have also the oxidative phosphorylation. Once the cell becomes actually deprived of oxygen, then we will actually switch to anaerobic, respiration. In this case, the only thing that will be available for it is going to be the glycolytic breakdown, that is going to render how many molecules of ATP? 2 only, right? So imagine from 30 plus to 2. All right, so what will happen actually once you no longer have ATP? All the pumps will fail. One actually specific pump that will fail is the NAK pump. So with this, you will see that the sodium will start to come in. What follows sodium? Water. So what will happen? The hydropic changes. That is going to be the first. That's going to be the first light microscopic finding of cell injury, cellular swelling. Okay, so you know where that came from, right? Right. So what happens as a result of another result of ATP deprivation. You know, the anaerobic glycolysis is going to be actually taking tap. And with this, you will see that there is activation of the PFK, which is going to stimulate the glycolytic pathway. Now, the cell is going to actually be depending on its glycogen store. It's going to break down the glycogen to produce, you know, the energy. The process of this is going to be the formation of lactic acid. So the pH of the cell is going to, you know, become depressed, right? So the cell will become more acidic. The enzymes in the cell need what you call optimal, you know, pH to work at. As a result of the acidity of the cell, those actually enzymes will no longer be working. And the result of that is some of the enzymes that are entrusted in maintenance of the cellular chromatin, of the nuclear chromatin, are going to be affected. In normal condition, the chromatin is finely dispersed in the nucleus. Once those enzymes becomes disrupted, you will start to see that there will be nuclear chromatin clumping. So instead of actually it being finely dispersed within the nucleus, it will start to create some clumps, which is the first and the only finding that you see in the nucleus in reversible cell injury. In reversible cell injury, that's right. So the nuclear chromatin clumping is going to be the first actually and the only finding that you will see in the nucleus in reversible cell injury. Now, you don't have protein, you know, once you no longer have actually ATP, again, maintenance of the ribosomes is going to happen. And as a result of that, you will start to see separation of the polysomes into monosomes. And as a result of that, production of protein is going to dip as well. Production of protein dips. Proteins are carriers of lipids. And as a result of that, you will start to see accumulation of lipid in the cell. That's going to result in the second finding that you see in reversible cell injury, which is fat change. All right. Now, you're no longer doing protein. Protein is needed for everything, including, you know, the buildup of the membranes of the cells, all the membranes of the cells. What will happen to the membranes of the cell? They will become weakened as well as a result of that. And now, actually, one very important, you know, result of the ATP deprivation is going to be the fact that actually the calcium is no longer going to be, the calcium pump is no longer going to be working. And as a result of that, you will start to see that there is an influx of calcium from the outside in. The picture is worth 1,000 words, right? That's exactly what we're going to find here. So ischemia, with the ischemia, there is going to be interruption of the oxidative phosphorylation that will result, actually, that will stop this process in its track and will start to form, actually, where the mitochondria will start to form ROS. The ROS are going to actually wreak havoc on the mitochondrial membrane. But before it does that, ATP production is going to dip. The pumps will fail. Okay, as you can see, starting with sodium, that's going to result in the hydropic change. There will be actually increased glycolysis that is going to take care of, you know, of the, trying to, bring some measures of ATPs to the cell, very meager amount of ATPs to the cells. The lactic acid will accumulate, pH will be depressed, and the nuclear chromatin clumping is going to ensue. There will be actually problem in maintenance of the ribosomes, so there will be ribosomal detachment, and the protein synthesis will dip as well. Yes.
In case of ATP depression, why would we have don't we need ATP for this?
Say it again, please.
We need ATP for these pumps to work. We need ATP for these pumps to work.
Yes.
So in case of ATP depression, why do we have, for example, cells growing? Why not shrink?
No, because the pump has failed. The Na pump has failed. The Na pump is at the surface of the cell, keeping the sodium out and the potassium in. Once it fails, what happened to the sodium? It will find its way into the cell. Okay, and when it finds its way into the cell, water will follow it, resulting in hydropic changes.
Yeah, but doesn't it need ATP for that?
Right. This is the entry of sodium is not happening through the pump, it's happening through the membrane because the pump has failed. Okay. All right, so if you restore oxygen, everything goes back to normal. At least, like this is what you would hope for in the early stages. If it continues unabated, irreversible injury will set you up. All right, so there is a point of no return. What is the point of no return? How about this? Actually, you can combine the point of no return that will take the cell from reversible and put it into an irreversible cell injury mode, and one-way cell, one-way street to the afterlife, if you will. That's going to be irreversible changes in the mitochondrial function. And if there is any problem with the structural integrity of the membranes of the cell in general, calcium, and finally, number 4, you may add it to it yourself, is any kind of nuclear injury beyond nuclear chromatin clumping. Okay, so any one of those 4 actually is going to take the cell into a one-way street into irreversible cell injury. Mitochondrial changes, structural integrity of the cell membranes, calcium influx, and 4 nuclear changes that are beyond the nuclear chromatin clumping. So the irreversible cell injury, again, what's happening here, when you talk about irreversible cell injury, the mitochondrial damage is going to be actually paramount here. Again, these are the power houses, the many factories of ATPs that without which the cell will not be able to live. Very critical players in cell injury and cell death. So what happened actually, when you have mitochondrial injury? One of the things that's going to happen is failure of the oxidative phosphorylation, as we have just talked about at length. And then formation of the reactive, species, oxygen species that we also have talked about as well. Now, not only this, actually, as a result of the injury that is happening in the mitochondria, and the fact actually that, the nucleus itself also has sensed that there are changes in the mitochondria that are, most likely going to be a life-ending changes of that cell. Then the nucleus is going to act by actually overexpressing a group of genes that will be translated into proteins. And those proteins are going to catapult themselves and insert themselves into the mitochondrial membrane, resulting in the formation of what is known as high conductance channels, also known as mitochondrial permeability transition core, MPT. All right, so remember this. So the mitochondria has been damaged. A message has been sent to the nucleus that the mitochondria is damaged. In the nucleus, there is always, that's by the almighty decree, there is always actually 2 groups of genes that take care of everything. One group that is pro-apoptosis, and the second group is anti-apoptosis. And they are always, during life, they are always in direct balance with each other. So what's going to happen when the nucleus will receive the message that the mitochondria has been injured, the nucleus is going to upregulate those genes that are pro-apoptosis. And those genes that are pro-apoptosis now are going to be translated into proteins in the form of channels that are going to be inserted into the mitochondrial membrane, known as the MPT. What will the MPT do? The MPT are going to do a couple of things. One of them, they will allow the content of the mitochondria to seep into the cytosol. One of the content of the mitochondria is calcium. That's bad enough because now calcium is in the cytosol. This is 1. 2, there is actually what you call a gradient between the mitochondria and the cytosol. This is going to be lost now after the MPT has formed. So that's going to disrupt further the production of ATP and further the oxidative phosphorylation. 3, this process is happening in the mitochondrial membrane. So the inner surface of the mitochondrial membrane where the oxidative phosphorylation is happening will stop in its track. And finally, the contents of the mitochondria will find, other contents of the mitochondria will find its way into the cytosol. And that, that's going to be, represented by the cytochrome C. and the cytochrome C are going to activate a group of enzymes in the cytosol that are known actually as caspases. And the caspases are going to actually put the cell onto one-way street towards apoptosis and death. Okay? This is simply, what we have just talked about here. Did you guys get it? So what will actually, the formation of the MPT do? Or, where does the MPT come from? From the message that, the nucleus have received, that the mitochondria is injured. So the nucleus, what does it do? It upregulates the pro-apoptotic, right? And it downregulates the anti-apoptotic, meaning the nucleus is setting the cell to die, okay? Now, those actually are going to be translated. They get translated into proteins. The proteins will be inserted into the mitochondrial membrane. Once that happens, you have what you call, when there is a gradient between two things. This is what I told you. Some English words sometimes, fail me for some reason, maybe because of age, unfortunately. So could you help me with that? When you have a gradient between two things, between the mitochondria. Thank you very much. Amazing. Thank you very much. Potential. So the potential between the mitochondria and the cytosol will be lost as a result of this MPTs. Okay? So this is what a young brain will do. I appreciate that a lot. You see how grateful I am actually when I'm reminded of something that I forgot. I'm serious, by the way. Because it's, I have been looking for this word from the boys' lecture and I could not find this. All right, so potential has been lost. This is one. Two, it is disrupting the inner surface of the membrane, right? Three, it is allowing for calcium to pass into the cytosol. And four, it's allowing cytochrome C to pass also into the cytosol. All of those are going to first simply take care of production of the ATP in the mitochondria. It will no longer be the case. Two, it's going to activate a lot of the degradative enzymes in the cytosol, okay? And three, it's going to be, activating, cytochrome C that's going to take care actually of the apoptosis process. So in a way, actually, if you think about it, now you have what you call competition of mechanisms to kill the cell. You agree with that? Could you see that? Because now calcium has been actually released into the cytosol, right? And ATP is no longer produced. What happened to the membranes and to the pumps? They fail, right? So more calcium now is in the cell. Okay, more calcium is in the cell. What does calcium do? Activate the degradative enzyme, or the lipases, or the proteases, or the ATPases, right? It will tear down pretty much everything. Okay, and it does that through the process of necrosis. But at the same time, the mitochondria has released the cytochrome C into the cytosol, correct? Which is gonna actually activate the apoptosis process. So now you have competition between apoptosis and necrosis. Which one do you think is going to be the winner of these competition? Apoptosis. Who says apoptosis? Who says necrosis? It is necrosis, of course. Always chaos wins the day. Apoptosis is a highly organized process that that actually needs energy to happen. Whereas necrosis is what you call a wholesale kind of killing. I used to actually tell it, being from the Middle East, I can actually talk about the Middle East. This is bad for the Middle East because I can talk about them, like I'm being from Syria, I can talk about Syria too, But so what I want to tell you, I always actually, liken apoptosis to, how death happens in civilized countries, It's a clean kind of death, They will call the mortuary, they will tell him, the person will die on, day so and so at 3 p.m. Okay, it's a clean kind of death. Whereas, the necrosis is what we call a third world kind of death. Usually it is wholesale, where there are probably millions of people dying at the same time and nobody really, give a damn about this. Just, my own black humor into this. You have to bear with me, actually. Sometimes it trickles. I try to control it as much as I can, but I cannot help it sometimes. Yeah, so necrosis will win the day for sure, no question about it. Why? Because it's quicker. Two, it does not spend any energy. Three, it's only dependent on calcium. There are no steps. When we get to the apoptosis, you will see that there are steps actually in it. First the initiating caspases are going to be activated, and then they have to activate the executioner caspases and take it from there. Go ahead. No offense for the third world, I'm part of it, so I can talk about it. Good. Go ahead. Speak up, please. Speak up again. I have no problem with my hearing. Right. No, the disappearance of the cell membrane, great question. Disappearance of the cell membrane is a feature of necrosis. Because with apoptosis, like I told you, it's a clean way to die, the Western way to die. There is no mess around, really. The cell is divided into smaller components that have a flag on top of it. It's like what you call a flag mark on top of it, that are going to be recognized by the macrophages. Each macrophage go and take one of those apoptotic bodies. But the cell contents are never opened up to the extracellular medium. Okay, it stays intact until the last moment. Simply divide into small pieces. I hope I did not offend anybody from the Middle East. Yeah. I'm sorry. Do you see what I'm saying? Okay, good. Further. Yeah. Yes.
But it was already activated for the
Yes. This is going to continue the process and augment the process. Further augment the process. So there's a massive force that the nucleus has been damaged. That the nucleus will respond to by creating this force. The force will allow the cytochrome, which is a higher level of commitment to death. Okay? So it's what we call it augmenting the process. Altering the process. Anything else? Good. Oh. All right, so damage to the membrane. What are the mechanisms? Someone asked me actually, what question do you ask in the POD? I gave an example actually. It is mechanism, really. Pathology, you learn pathology in medical school because you want to know how things happen. And as physicians, you have to know how things happen because that will tell you how things will unhappen, right? And this is what is meant by that, really. So mechanism, focus on mechanism. Whenever you see it, try to get to the bottom of it to understand it inside out. So what are the mechanism of injury to the membrane? How does the membrane of the membranes, right? Really, not just one membrane. There is the mitochondrial membrane, the lysosomal membrane, then the plasma membrane. How does it happen? One, ATP is no longer being produced, right? So how about the protein production? Is there any protein production? No. So you have no longer spare parts, if you will, that is going to take care of that. And now you have actually activation of the phospholipases. Why? Because the membranes are leaky, allowing for calcium. Calcium goes in and activate the phospholipases that will break down further components of the cellular membranes. Now remember, the mitochondria is damaged and now is producing ROS. ROS itself has a tendency to interact with specifically two components in the cell. One of them is cellular membrane, two nucleus. It goes after the two most critical components of the cell, that are the ROS. Are you guys with me? So first, no ATP is there, so there is no production of ATP. So no protein is being made. Two, calcium is being let in, activate the phospholipases that will tear down the membranes of the cell. Now, free radicals are being produced, by the mitochondria. That also is going to actually wreak havoc on the membranes. Now, there is also activation of the proteases. The proteases will tear down the cytoskeleton. And now you have accumulation of lipid bioproducts. All these lipids that are accumulating in the cytoplasm are itself actually toxic to the cell. This is number one. Two, actually, they may exchange with components in the cell membranes. And when they do this, they are going to change the permeability, increase the permeability, and accelerate the demise of the cell. and also, change the potential again of that cell with the extracellular medium. All right, so where does that happen? Mitochondrial membrane injury. Imagine this. This is the site where the ATP is being produced. Now it is being damaged. This is one that is going to be actually detrimental to the continuation of the cell, if you will. Plasma membrane. Imagine, the plasma membrane, that the house, that was housing all this stuff in its midst is no longer there, allowing things to go out and allowing things to come in. That is going to be bad enough because calcium will be coming in and all the, needed components for cell, cell continuation, cell life are going to be, let out of the cell. And now finally, actually, the lysosomes are going to be also, the lysosomal membranes are going to be affected. And when the lysosomal, membranes are affected, what will happen to those enzymes in those vacuoles? They will be released. Calcium is there, they will be activated, and they will start to actually wreak havoc on the cell itself. This is it. Thank you very much. Attendance. You wanna stop sharing, or what do you do? Really? Stop sharing? Just stop sharing? And then end?